In this video, I will show you how to find limits algebraically. If you appreciate the content, please give it a like. We can think of finding limits as a flowchart of possible tools we might use, but the first tool to try is always direct substitution. Direct substitution means simply plugging in the value that x is approaching in place of x. If you don't get 0 over 0 or infinity over infinity, you will have an answer. To find the limit as x approaches 0 of f of x, we first try plugging in 0 for all the x's, which brings us here. Of course, that just leaves -1 in the numerator. These two terms are gone. So we have -1 over -3, which simplifies to positive 1/3. If direct substitution gives you a numerical value, that is the limit. To find the limit as x approaches -3, we plug in -3 for all the x's like this. This simplifies to -4 over 0, which will lead to an answer. However, first we need to correct this notation. This expression is undefined, and you're not allowed to write down an undefined expression in your work at all. So if you put equals -4 over 0 like this, you're going to lose the point on the AP exam and on my test if you're my student. So instead, what you need to do is make some arrows like this. So we're going to say, look, the numerator is approaching -4, and the denominator is approaching 0. This is allowed. Notice I'm avoiding writing the undefined expression -4 over 0, which is like illegal. When the numerator approaches a constant while the denominator approaches 0, the limit does not exist. Do not put an equal sign in front of the d and e. This will lose you a point. If we use direct substitution to try to find the limit as x approaches 1, we plug in 1 for all the x's, and we get this. However, we notice that the numerator is going to be 0, while the denominator is also going to be 0. This is called the indeterminate form, and you will lose a point if you write down equals 0 over 0. So don't do that. Instead, like before, use arrows. If direct substitution gives you an indeterminate form, like 0 over 0, infinity over infinity, or infinity minus infinity, it does not mean that the limit does not exist. The limit might exist, or it might not exist. We don't know yet. We have to keep going using other methods. I'm going to move on to other problems now, but I will come back to this example in a little while. F of x is a piecewise function that switches from one function to the other at x equals 2. To find the limit of f of x as x approaches 2 from the left, the top piece of f of x applies. So we need to find the limit as x approaches 2 from the left of 3x minus 1. We can find this by direct substitution. If we plug in 2 for x, that's 3 times 2 minus 1, which is 6 minus 1, which equals 5. When we talk about the limit as x approaches 2 from the right, we are talking about values of x that are greater than 2. So the bottom piece will apply. So we need to find the limit as x approaches 2 from the right of x squared minus 3. Again, we can find this by direct substitution. If we plug in 2 for x, we get 2 squared minus 3. That's 4 minus 3, which is equal to 1. So that's the limit. The overall limit as x approaches 2 of f of x only exists if the limit from the left is equal to the limit from the right. Since the left-sided limit and the right-sided limit are two different numbers, the overall two-sided limit does not exist. Remember, don't put an equal sign right here. If you're trying to find a limit and direct substitution gives you 0 over a constant, the limit is equal to 0. If direct substitution gives a constant divided by 0, then the limit does not exist. If direct substitution gives you a constant divided by itself, then anything divided by itself is 1. If you're trying to find the limit as x approaches infinity, and you get infinity over a constant, the limit is infinity. This makes sense because the numerator is growing bigger and bigger, while the denominator stays a constant. It stays small. So the overall value of the fraction is getting bigger and bigger and approaching infinity. Or you can simply say, does not exist. If you get a constant over infinity, the limit is 0. That's because if the numerator stays small, while the denominator gets bigger and bigger and bigger, the overall value of the fraction gets smaller and smaller, closer and closer to 0. Again, if you get a constant over a constant, that's equal to 1, assuming you have a constant divided by itself. If you get an indeterminate form like 0 over 0 or infinity over infinity, it does not mean that the limit does not exist. It might exist or it might not. You have to keep going using other strategies. To review, when trying to find a limit, we always start with direct substitution. If direct substitution gives you a real number, that answer is the limit. If direct substitution gives you a constant divided by 0, then the limit does not exist. However, if you get an indeterminate form like 0 over 0, infinity over infinity, or infinity minus infinity, then you have to keep going using other strategies. Here's the example we ran into earlier, where direct substitution gave us 0 over 0. Once again, let me emphasize, do not write equals 0 divided by 0 anywhere on your paper. That will lose you a point. Instead, use arrows like this. One strategy to keep going and try to find the limit is to factor and cancel. The denominator factors as x minus 1 times x plus 3. We notice that we have the same factor of x minus 1 in the numerator and in the denominator. We can cancel out factors like this without changing the limit. So the original limit is equal to the limit as x approaches 1 of 1 over x plus 3. Let's try direct substitution again. Plugging in 1 for x gives us 1 over 1 plus 3, which equals 1/4. Since we did not get an indeterminate form, we have our answer. Here's a new problem. First, we try direct substitution. We get 4 to the third power minus 64 over 4 minus 4. We quickly see that we are going to get 0 over 0, an indeterminate form, and we have to keep going. Let's try the factor and cancel method again. 64 is 4 to the third power, so the numerator is the difference of two cubes. In a previous course, you should have learned how to factor the sum or difference of two cubes. The difference of two cubes always factors as a binomial times a trinomial. The binomial is just the cube root of each of these terms. So if we begin with a cubed minus b cubed, the binomial is a minus b. If you square these two terms, it gives you the first term and the last term of the trinomial. So a squared plus b squared. The middle term will be the product of these two terms, except it will be the opposite sign. So a times b, and positive because it's always the opposite. This basically gives you a formula for factoring the difference of two cubes. It also works for the sum of two cubes. For the sum of two cubes, the binomial is a plus b, and the middle term of the trinomial is negative. Some teachers like to use the acronym SOAP to remind students how the signs go. These letters stand for same, opposite, always positive, because compared to the original expression, the first sign is the same, the second sign is the opposite, and the third sign is always positive. We can factor x cubed minus 64 as a binomial times a trinomial. The binomial will be the cube root of each of these terms, so x minus 4. If you square each of these terms, it gives you the first and last term of the trinomial. So the first term will be x squared, and the last term will be a positive 16. The middle term will be the product of these two terms, but with the opposite sign. So plus 4x in the middle. Now we factored it. The trinomial is almost never factorable, so don't bother trying. We can cancel out the factors of x minus 4 from the numerator and the denominator without changing the limit. So the original limit is equivalent to this new limit. This new limit can be evaluated by direct substitution without getting an indeterminate form. So the limit is 48. Limits like this, with an f at x plus h in it, are very common in calculus because they lead to something called a derivative, which we will learn about in the next unit. Students often struggle with these problems because they mess up the algebra. To fix this, I strongly recommend that you evaluate f at x plus h separately and sort of first. So here's f of x right here. Quick side lesson, if I say what is f at 7, you know that would be 7 squared. If I say f at, let's say, pi, that would be pi squared. If I say what is f at smiley face, that would be smiley face squared. Similarly, f at x plus h means x plus h squared. What you're not going to do is try to write this as x squared plus h squared. That is some bad algebra. Instead, we need to expand this. X plus h squared means x plus h times x plus h. This gives x squared plus 2xh plus h squared. So this is f at x plus h. Now we are ready to write the limit as h approaches 0 of f at x plus h minus f of x over h. Let's substitute this expression that we just found for f at x plus h. So we will have x squared plus 2xh plus h squared. And then minus f of x. Well, f of x is x squared. So minus f of x is just minus x squared. Notice that we have x squared, and then we have minus x squared. So these two terms will cancel each other out. The limit simplifies down to this. What you're not going to do is cancel out these h's. Again, that is some bad algebra. You cannot cancel out terms that are connected by a plus sign or a minus sign. That's probably the most common mistake that I see. Instead, we factor out the common factor of h from the numerator. So factoring out that h and putting it in the front leaves 2x plus h. And then over h. Now this h is multiplied by the factor of 2x plus h. Now you can cancel out these h's because it's connected by multiplication, not addition. So the limit simplifies down to this. By the way, notice that every step I keep writing the limit as h approaches 0 over and over and over again. This is mandatory. You have to keep writing the limit as h approaches 0 while you simplify this expression. You have to stop writing the limit as h approaches 0 the moment you do the direct substitution, which is what we are about to do right now. So plugging in the 0 gives us 2 times, wait, I almost plugged in for the wrong thing. H approaches 0, not x. So I'm going to have 2x plus 0. And now we just did the direct substitution, so now is the moment when we stop writing the limit as h approaches 0. Of course, this 0 is not doing anything, and the final answer is 2x. It is fine that this limit is not a constant. It's allowed to have an x in it. Very common. We were finding the limit as h approaches 0, so your final answer can't have any h's in it. For this example, when we try direct substitution, we end up with 4 minus 4 over 2 minus the square root of 4. You can see that we are going to get 0 over 0, which is an indeterminate form, and we need to keep going using other strategies. When the expression involves a square root, a good strategy to try is rationalizing. That's rewriting to get rid of the square root from wherever it is. I'm going to get rid of the square root from the denominator, and it will still be in the numerator, but I might get something that does not give me an indeterminate form. The way you rationalize is by multiplying by the conjugate. The conjugate of a minus b is a plus b. So the conjugate of 2 minus radical x is 2 plus radical x. This is only valid and legal if we multiply the same thing in the numerator and the denominator. So I need to multiply by 2 plus radical x in the numerator as well. The beauty of multiplying by the conjugate is that you will always get a squared minus b squared. The middle terms always cancel out. In the numerator, I'm going to leave these factors alone and write 4 minus x times 2 plus radical x. But in the denominator, I'm going to write a squared minus b squared. This is my a and this is my b. So a squared is 4 and minus b squared. If I square radical x, I get plain old x. So a squared minus b squared is 4 minus x. And look what we have here. The same factor of 4 minus x is in the numerator and the denominator. We can cancel out this factor without changing the limit. Remember, keep writing the limit as x approaches 4 over and over again until you do direct substitution. We are about to do direct substitution right now, so we stop writing the limit as x approaches 4. We get 2 plus the square root of 4. To be clear, this is a valid answer for AP Calculus. However, it feels silly to stop here. The square root of 4 is 2, so we have 2 plus 2, which is 4. For this problem, what happens if we try direct substitution? We get 3 minus the square root of 2 times 1 plus 7 over 1 minus 1. Obviously, in the denominator, that is 0. Here we have 2 plus 7, which is 9. The square root of 9 is 3. So that's 3 minus 3, which is, again, 0. 0 over 0 is an indeterminate form, so we have to keep going. Let's try rationalizing again. This time the square root is in the numerator, so let's multiply by the conjugate of the numerator, which is 3 plus radical 2x plus 7. To keep it legal, we have to multiply by the same thing in the denominator. 3 plus radical 2x plus 7. When you multiply by the conjugate, you're going to get a squared minus b squared. So we have the limit as x approaches 1. And a squared is 9 minus b squared. If I square this term, the radical goes away. So I'm going to have simply 2x plus 7. Please be careful right here. A super common mistake is to write this without parentheses, which is wrong. That's bad algebra. You either have to include parentheses on this step, or you need to go ahead and distribute this negative sign, which is going to cause this plus to become a minus. 9 minus 7 is 2. So we end up with negative 2x plus 2 in the numerator. At this point, we notice that the numerator is factorable. There is a GCF of 2. Let's factor out negative 2, actually. So that will leave behind x minus 1 on the inside. Now we notice the factor of x minus 1 in the numerator and the denominator. Of course, we can cancel out the factor of x minus 1 without changing the limit. Now we can find the limit by direct substitution without getting 0 over 0. Plugging in 1 for x gives us negative 2 over 3 plus the square root. 2 plus 7 is 9. This is technically a valid answer for an AP Calculus class, but we can go ahead and say negative 2 over 3 plus 3 is 6, which reduces to negative 1/3. If we plug in 0 for x, we have 1/3 minus 1/3, which is 0. And obviously, if x is approaching 0, the denominator is approaching 0. The indeterminate form means we have to keep going. When you see the sum or difference of two fractions, your instinct should be to make like denominators and combine the fractions into 1. So I'm multiplying by x plus 3 over x plus 3 on the right and 3 over 3 on the left to make these like denominators. When you combine the fractions into 1, either use parentheses around the x plus 3 to show that we have not distributed the negative sign yet, or remove the parentheses and distribute the negative sign to make minus x minus 3. A common mistake is to leave it like this and have 3 minus x plus 3, which is wrong and will not work out correctly. So on the next step, we notice that we have 3 minus 3. These terms will cancel each other out. That leaves us with negative x over 3 times x plus 3, all of which is divided by x. Quick side lesson, when you have a over b and then you're dividing by c, you get a over b c. In other words, when you divide a fraction by something, whatever you are dividing by ends up multiplying in the denominator. For example, 2 over 3y divided by x will be 2 over, here's my 3, here's my y, that x is going to end up multiplying in the denominator. So 2 over 3xy. Similarly, when we divide this blue fraction by this orange x, the x ends up multiplying into the denominator like this. At this point, we suddenly recognize that we have this common factor of x in the numerator and in the denominator. These will cancel each other out without changing the limit. So the original limit is equivalent to this limit. Let's try direct substitution again. Plugging in 0 for x gives us -1 over 3 times 3, which is -1/9. Once again, notice that I had to keep writing the limit as x approaches 0 over and over again until I got to the direct substitution. As soon as I plugged in 0 for x, I had to stop writing the limit as x approaches 0. To review, if we get an indeterminate form, we keep going by using algebraic techniques like factor and cancel, rationalize, or other algebra like forming like denominators and combining into a single fraction and hoping something cancels out. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.